This video is for people that get surprised by biology. These are the characteristics of every respiratory surface. They all have a high surface area to volume ratio because the higher the surface area to volume ratio, the higher the exchange. They are thin because the gases, if they don't have to travel as far, they can travel quicker. If the gases dissolve in liquid, they will diffuse faster through a membrane. A rich blood supply keeps up a nice concentration gradient because diffusion requires a concentration gradient. And all respiratory surfaces need support to hold the exchange surface open, and only mammals have surfactant that stops or reduces the surface tension of the water, stopping droplets, and forms a thin sheet. Right, the next one we'll do is insects. Insects have an exoskeleton made of chitin. On the surface of their body, they've got spiracles, which are openings for the gas movement. They've got hemolymph, which is like their blood. We call it bug juice. The tube running down to the tracheal pits is called a tracheal tube. The tracheal pit has water in it, and that is the respiratory surface. Just diffusion. Not very efficient, though. Echinoderms have spikes. They have a calcified exoskeleton, and inside the spikes they have blood vessels, and then on the outside they have water, and that allows for quite efficient gas exchange. All right, amphibians have two respiratory surfaces. Both are quite simple. They have a simple lung structure, and they have skin, and they both have exactly the same characteristics, but they don't work very well by themselves. Then we'll talk about fish. Fish take in water through their mouths, and it goes out through the operculum on the side. It goes over the gill arches that are made of bone. On the bones are little fluffy pink structures called lamellae that have blood vessels in them, and that's where the gas exchange takes place. The fish use countercurrent exchange, which is very, very efficient. The medium, and in this case, it's water, it's full of oxygen as it goes in, and the blood that's coming in from the opposite direction has no oxygen in it, and we have the constant gradient for exchange that makes it very, very efficient. The amount of oxygen in the water can vary. Fresh water has more oxygen in it than marine. Running water has more oxygen in it than still water, and cold water has more oxygen in it than hot water. Now, birds use the best of both. They have both static, like us, and countercurrent exchange. When air goes in the first time, it goes through these structures that are held open called air capillaries, and we have static exchange. Static means going 100% into zero, which ends up being 50-50. All right, so we have the static exchange like us, because the blood and the air are traveling in the same direction through the air capillaries and ending up in the air sacs that are inside the hollow bones. Then the air sac contracts and pushes the air back against the blood, and so that's countercurrent exchange, and it extracts all of the oxygen out of the air.